Welcome back, innovators, to another deep dive explainer right here at Idea Mechanics. It is absolutely fantastic to have you with us today. As always, our lead innovation catalyst, our brilliant navigator, is here with us, ready to guide us through today's visual breakdown. Now, before we really get into it, for those of you who are new to the team, TRIZ is this incredibly powerful, systematic methodology. It proves that innovation isn't just some random event, it's a structured, repeatable approach to solving what look like completely impossible engineering contradictions. Today, we are going to completely transform how you approach complex motion and force transmission. We're diving deep into TRIZ Principle 24, mechanical translation and the architecture of strategic intermediaries. All right, let's get right into it.
So picture this situation, one we've honestly all faced in advanced engineering. You got two completely mismatched components, and you desperately need them to interact. What's the standard knee-jerk response? Well, it's usually that frustrating, incredibly expensive trial and error trap. Teams try to just force physically mismatched objects to interact directly. And you know what happens? You end up with massive friction, super bulky designs, complex system redesigns, and ultimately, mechanical failure. It's just an exhausting way to build. So the big question is, how do we actually bridge these impossible mechanical mismatches without tearing down the entire system and starting from scratch?
Well, the answer definitely isn't waiting around for a random eureka moment. If you're ready to stop relying on luck and start mastering systematic discovery, hit that subscribe button to join the Idea Mechanics team.
And don't forget to ring the notification bell so you're the very first to see our next innovation breakdown. We really want to build this culture with you. Drop a comment below and tell us which TRIZ principle or tech challenge we should tackle next.
All right, let's jump straight into Section 1, Escaping the Direct Trap.
To really escape this trap, we kind of have to shift our entire mindset. Think about advanced robotics, aerospace, or automotive design. Forcing two mismatched objects to directly interact, especially when they have totally different shapes, sizes, or types of motion, is literally a recipe for disaster. That's exactly what leads to those incredibly fragile, clunky designs. We need to move away from that exhausting reality and toward a disciplined, repeatable architecture. You can see the stark contrast our innovation catalyst is pointing out right here. On one side, we have the old way, forced mechanical mismatches. That's where you're basically fighting against physics. On the other side, the new way, strategic operational bridges. This is the true essence of systematic innovation. We aren't guessing anymore, right? We are engineering a flawless transition between totally incompatible states.
And that brings us to the absolute core of our lesson today, TRIZ Principle 24, also known as the intermediary. The strategy here is wonderfully simple but incredibly powerful. Instead of completely redesigning your mismatched components, you systematically introduce a third object or process. You bring in a strategic middleman. This intermediary instantly overcomes any mismatches in material properties or motion types. It ensures that complex interactions happen smoothly, reliably, and most importantly, without causing any harm to the overall system.
So let's put this into practice. Section 2. Case study, motion converter for the in-pipe robot.
We're shifting gears into a high-tech breakdown to look at a very real-world robotics application. Check out this first contradiction our navigator is highlighting for us. Engineers were tasked with designing a single-drive peristaltic in-pipe robot for inspection purposes. The challenge? A classic mechanical mismatch. The robot's motor provides rotational or rotary motion, but the robot's legs? They require linear motion to effectively crawl their way through the pipe. So how on earth do you force a spinning motor to push a leg in a straight line without relying on a massive, heavy gearbox?
Let's look at the systematic sequence our catalyst has designed to solve this exact problem. Step 1, the motor rotates. Step 2, instead of a total redesign from the ground up, the engineers simply introduced a crank slider mechanism, specifically a basic connecting rod. And let me tell you, this rod is the ultimate middleman. Step 3, the rod seamlessly transfers that rotational motion into the linear motion of the slider, translating the force perfectly. It elegantly solves a highly complex mismatch without adding any unnecessary bulk or points of failure to the robot.
We're ramping up the stakes now. Section 3. Case study, adaptive link with the telescopic shaft.
Here's our next contradiction mapped out for us, facing that exact same in-pipe robot. The core problem here is the peristaltic motion itself. The robot needs to transmit continuous power from the motor at the rear all the way to the front. However, to actually inch through the pipe, the robot's body is constantly changing length. It's stretching out and compressing back in.
So you have a dynamic, ever-changing distance, but you absolutely need continuous power. A rigid direct connection shaft is physically impossible here, right? Because it would either snap under the pressure or completely restrict the robot's ability to move. To bridge this impossible physical gap, they applied Principle 24 all over again. Step 1, the rear motor generates the power. Step 2, the engineers introduced a telescopic transmission shaft. This flexible middleman can extend and contract, perfectly accommodating the constantly changing length of the robot's body. Step 3, the power transmits perfectly to the front. The robot maintains full mobility and functionality, all because of a brilliantly designed intermediary.
Which brings us to our final section, Section 4, Mastering Systematic Innovation, Repeatable Architecture.
Because at the end of the day, true mechanical intelligence really isn't about brute force. It is all about repeatable architecture. As our navigator is proudly showing us, here are your key takeaways for the day. First, innovation is a repeatable architectural skill. We've proven today that solving impossible constraints is a systematic, structured process. Second, you must master the art of the middleman. The most advanced robotic and automotive systems out there, they don't just force mismatched components together. And third, stop fighting mismatched motions. By aggressively applying Principle 24, we systematically deploy clever tools like connecting rods or telescopic shafts to bridge literally any gap.
So I'm going to leave you with this final provocative challenge for your very next big project. Where can a strategic middleman solve your current design mismatch? Take a hard look at your workflows, your hardware, your complex systems. Stop trying to force a direct connection where one doesn't belong, and start engineering your intermediary. Thank you so much for joining us on Idea Mechanics. Keep building, keep innovating, and we'll catch you in the next explainer.